Hello everybody. This is our week 4 lesson, and in this lesson we are going to study Boolean functions. As we saw in the example of classical cryptosystems, the ciphers can be represented by mathematical expressions. As we defined earlier, cryptography consists of mathematical methods and it aims on ensuring the basic purpose of information security. And when we talk about the purpose of information security, we mean confidentiality, integrity, authentication and non-repudiation. The basic design principles of secret key cryptosystems are confusion and diffusion. The principle of confusion underlines the importance of hiding the overall structure of cryptosystem, while diffusion suggests that uncertainty is spread out evenly over the whole system. In this section, we are going to study basic mathematics, which will help us to understand the working principles and proofs of security levels of modern cryptosystems. We are going to start with Boolean functions, since they are the basic components in most of secret key cryptosystems. In mathematical notation, we can consider a cipher as an algorithm or function which takes a plain text as an input and outputs a ciphertext. The second parameter which is taken as an input is of course a cipher key. In digital devices, each symbol of an information is represented by using 8-bit sequences. These sequences should satisfy some security criteria such as nonlinearity, correlation immunity, and should have high algebraic degree and so on. However, some criteria are mutually inverse, that is, if one criterion increases, the other is decreasing. For example, the speed of an algorithm and its complexity are mutually inverse. The higher the complexity of an algorithm, the lower the speed of the algorithm. Here we have the same situation. Thus, there is always a trade-off between some of security criteria. However, to proceed further, let us first define some basic concepts of Boolean functions. A Boolean function is a function which maps n bits into a single bit. Boolean functions are always calculated over a finite field f2. The term finite fields is new in our lesson, so for now, let's define a finite field f2 as a set of elements modulo 2. As we know from our previous lectures, if we define a set of integers modulo some integer, then this set is going to consist of elements which are less than the defined modulo. So, using this logic, we can deduce that in the field f2, elements can be numbers which are less than 2, that is 0 and 1. We can name them as bits. So, a Boolean function is a function which maps a sequence of bits into a single bit, and this n in our expression defines the length of this sequence. Another notation that we can use for expressing a Boolean function is this notation. It means that we have a sequence of zeros and ones of length n, which are mapped to a single element which can take values of either 0 or 1. To represent a Boolean function, we can use its truth table representation. As we said before, a Boolean function is a function which maps n bits into a single bit. If for all possible sequences of length n, we compute these single outputs by which we can define n binary inputs, this vector is a truth table of a given Boolean functions. That is, the truth table of a function f is the evaluation of function f for all possible inputs. Thus, if a Boolean function has two variables, the size of corresponding truth table will be 2 to the power 2, since for 2 bits there are totally 4 possible 2-bit sequences. For 3 bits, for example, there will be 2 to the power 3, which is equal to 8 possible sequences, and these sequences are listed here. These sequences are 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on up to 1, 1, 1. That is, if a Boolean function has an input of three variables. One of possible truth tables is a truth table given in this slide. And if the corresponding values of input for a function are ordered lexicographically, that is for a decimal input 0, then for decimal input 1, and so on up to 7, we have output values ordered according to this lexicographical order, then this vector is called a truth table of a Boolean function. Sometimes it is useful to use polar representation of a Boolean function, which is denoted by f cap. In polar representation, ones are mapped to minus ones and zeros are mapped to plus ones. Formula for transpose from truth table to its polar representation is given here. Thus, if a Boolean function is given by its truth table, which can be represented as an output of a function evaluated at 0, at 1, and so on, then its polar representation can be obtained by this formula. That is, we take minus 1 to the power of evaluation the Boolean function for each possible value ordered lexicographically. So, in the polar representation of a function, we map ones to minus ones and zeros to ones. However, it is not always convenient to represent a Boolean function by its vector representations such as truth table or polar truth table. A Boolean function of n inputs can be represented in minimal XOR of products form, since, for example, if we have an 5 input bits, then the length of truth table is going to be 2 to the power 5, which is 32 bits. And as the number of bits in input of a Boolean function increases, the length of truth table is going to increase significantly. So the so-called algebraic normal form is a more convenient way of representing a Boolean function. An algebraic normal form is the representation of a Boolean function in some polynomial form, where we can terms of the first degree, terms of the second degree, so on up to terms of degree n. The coefficients a0, a1, and so on show if the corresponding term is present in the algebraic normal form or not. The algebraic degree of a function is the size of the largest subset of inputs associated with a non-zero coefficient. So, for example, in this general algebraic normal form, if this coefficient is equal to 1, then the degree of a Boolean function is going to be n. For example, let the number of input variables be equal to 2. Suppose that the truth table for Boolean function is given as 1, 1, 1, 0. Then its corresponding algebraic normal form is going to be 1 plus x1 multiplied by x2, because if we substitute each value of x1 and x2 to this formula, we are going to obtain this truth table of 1, 1, 1, 0. For example, let's x1 and x2 be 0 and 0 as it is in the first row of our table. Then the corresponding result is 1. It's easy to see that if x2 is equal to 1, then x2 multiplied by x1, that is 1 multiplied by 0, will give us 0, plus 1 will result in 1, and so on. So we can say that 1 plus x1 multiplied by x2 and the truth table 1, 1, 1, 0 represent the same Boolean function. For every Boolean function, there exists its algebraic normal form representation, and it is always unique. Calculation of algebraic normal form from its truth table requires O of n multiplied to 2 to power n operations, which is quite expensive. So let's consider an example of finding the values of Boolean function, which is represented by algebraic normal form x multiplied by y plus z prime. Here z prime means the complement of the element z. The corresponding two-stable representation of a Boolean function can be calculated as follows. Here we have x multiplied by y. If x and y are zeros, here we are going to have 0. So z prime is going to be equal to 1. 0 plus 1 will result in 1. Using the same logic, we can calculate all the other terms. So, the corresponding two-stable representation of a Boolean function given by algebraic normal form x, y plus z prime is this values of 1, 0, 1, 0, 1, 0, 1, 1. This is the truth table of a given Boolean function. So, as we can see from this example, calculating the truth table from a given algebraic normal form is very easy. Let us consider how to calculate algebraic normal form if only this kind of truth tables of a function is given. The situation when we have only the truth table of a Boolean function and we need to derive from this truth table an algebraic normal form is quite possible, since for cryptanalysis we usually intercept the sequence of bits but never the algebraic normal form by which this sequence is produced. So, if the truth table of a Boolean function is known, it is fairly straightforward to derive the algebraic normal form of a Boolean function. As we defined earlier, the general form of algebraic normal form is given by this formula. The constant term a0 is easily derived, since it corresponds to the case where all bits are zeros. Indeed, if we suppose that all x's are equal to 0, then we are left just with this a0 term. So therefore it is so easy to derive. To determine other coefficients ak, we can consider the following cases. For example, to derive the a1 term, we can use a Boolean function evaluated at point where x1 is equal to 1. Starting from this part of equation, all the terms are going to be equal to 0, so we are left with only this part of equation. From this part we can easily derive the term a1, which is equal to a0 plus f of x evaluated at the point 0, 0. All elements except for x1 are zeros. Using the same logic we can derive all the other terms. After we compute the linear part of equation, we can determine ajk coefficients, which are coefficients for the terms of the second degree. Thus, to calculate the algebraic normal form of a Boolean function, we need to calculate the corresponding coefficients a0, a1, and so on. Suppose that our Boolean function has only two inputs, x1 and x2, then the algebraic normal form can be of this form, and if we derive these coefficients a0, a1, a2, and a12, then we can find its algebraic normal form. There are two practical methods for calculating algebraic normal form from the truth table. The first method is calculation of algebraic normal form using some special matrix an. Let f be the truth table of n variable Boolean function, and let s denote the vector of coefficients. Then we can find this vector of coefficients by multiplying the truth table vector by some special matrix an and doing all the calculations modulo 2. The matrix AN can be calculated recursively by increasing its size. For example, at the first step, matrix A1 is equal to 1, 0, 1, 1. At each recursion, we increase the size of this matrix by rewriting the lower sized matrix to its first, third, and fourth quartiles and filling the third quartile by zeros. Let us show the calculation steps by an example. Suppose that the choose table of a Boolean function is given by 0, 0, 1, 1, 1, 0, 0, 1, and we will try to find algebraic normal form of a Boolean function for which the choose table is defined as we said before. All we need to do is first construct a matrix of a proper dimension. Our truth table is 1 by 8 vector. Thus we need the size of the matrix A to be 8 by 8. In the previous slide we saw how to increase the size of this matrix to 4 by 4. To increase its size to 8 by 8 matrix, we should rewrite this 4 by 4 matrix to the third and fourth quartiles of our matrix, and the third quartile should be filled with zeros. So if we do all these operations, we are going to end up with this matrix. As we can see, the first quartile, the third and fourth quartiles are similar, and only the second quartile is filled by zeros. So if we prepare an ordinary vector by matrix multiplication and we take the resulting vector modulo 2, we are going to obtain our desired vector of coefficients. Each element of this vector of coefficients are coefficients of Boolean functions a0, a1, a2, a1, 2, and so on. As we can see, coefficients a2, a3, and a13 are equal to 1. Thus, the algebraic normal form of a Boolean function is defined as x2 plus x3 and plus x1 multiplied by x3, since only these coefficients are equal to 1. Other coefficients are equal to 0, so the other terms are going to be cancelled because multiplication by 0 will give us 0. This is another example. Here we have a truth table given by 1, 0, 1, 0, 1, 1, 0, 1. The result of multiplication gives us this vector of coefficients. So that means that coefficients a0, a1, and the last three coefficients are equal to 1, so we end up with the algebraic normal form of 1 plus x1 by x3, which corresponds to this one, plus x2 by x3 plus x1, x2, x3. As we can see from the algebraic normal form, the algebraic degree of this Boolean function is equal to 3, because 3 is the size of the largest subset of inputs with non-zero coefficient. So this algorithm for retrieving algebraic normal form from the truth table is quite simple. However, as the number of input variables increases, the size of this AN matrix is going to increase, so it is quite time-consuming operation to compute the algebraic normal form of a Boolean function using this method. There is another method for computing algebraic normal form from its choose table, which is called a butterfly algorithm. In this algorithm, depending on the size of a truth table, which is given by 2 to power n, where n is the number of input variables, there will be n plus 1 calculations, and at each calculation we are going to find a new vector. So we write a truth table as a column vector. At the first step, we calculate the odd numbered elements of a new vector by simply rewriting the elements themselves. So these odd numbered elements are this element, this, and this. As arrows show, we just rewrite these elements. To calculate even numbered elements, we sum it with the previous odd numbered element modulo 2. That is, we pair ith element with I minus first element. So at this slide we can see the results of calculation of the first new vector. Using the same logic, we can calculate the second new vector. However, to calculate the second new vector, we are going to rewrite first two elements, and the next two elements are going to be calculated as the sum of the element with the I minus second element. It's easy to follow up this logic by these arrows. So using again the same logic, we are going to calculate the third vector. Here we rewrite the first four elements. You may have already noticed that in calculation by butterfly algorithm there is some pattern. So for the calculations in the vector 1, we have one element rewritten and the second element calculated. For the calculations of the second vector, we have two elements rewritten and two elements calculated as a modulo 2 addition of these elements with the previous elements. And for the calculation of elements of vector 3, we have four elements rewritten. If we had the fourth row, we would just rewrite these elements. Therefore, we can stop with the third vector. So the result obtained in the third vector is our desired vector of coefficients. As we can see, this result goes in line with the result obtained by the previous method, and the resulting algebraic normal form for a Boolean function given with this truth table is, as we defined it already using the first method, is x1 plus x3 plus x1 x3, because again we obtained the coefficients a2, a3 and a13 to be 1. So this is how we calculate the algebraic normal form if only the truth table of a Boolean function is given. Here we have another example. So as I said before, we start with truth table written as a column vector. At the first step we rewrite the first element as it is and calculate the second element as an XOR of first and second element. Rewrite this element, calculate this element by XORing 1 and 0. Rewrite this element 1 and 0 is calculated as an XOR of 1 and 1, and so on. At the second step, we should rewrite two elements, and these two elements, next two elements, are calculated. For calculation of this 0, we used this one and this one. To calculate this element, we XORed this element with this element, and so on. And the resulting vector of coefficients is 1 1 0 0 0 1 1 1, which gives us the algebraic normal form of 1 plus x1 plus x1 x3 and so on. So as you can see, calculating algebraic normal form from the truth table is not as straightforward as calculation of truth table from algebraic normal form. So the next question we are going to consider is the number of Boolean function of a given degree. For example, suppose that a Boolean function has 2 bits input. Then for 2 bits input x and y, for 2 bits x and y, we have only 4 possible sequences, which are 1 1, 1 0, 0 1, and 0 0. The number of different Boolean functions of degree 2 is 2 to power 2 to power n. Sorry, this n should be written as a power of this 2. So if we have 2 input bits, then the number of possible Boolean functions is 16. So with this diversity of Boolean functions, even for 2 input bits, we have 16 Boolean functions. So with this diversity of functions, we need to define security criteria which would help us to choose the secure ones while implementing encryption algorithm. At the second video of this lesson, we are going to consider the security properties of Boolean functions.